Hey, welcome back. In this video, we're going to talk about modeling with sine and cosine, but in a little bit different way. Importantly, in this video, we're going to talk about if we have a changing midline or equilibrium. Previously, when we talked about the models using sine or cosine, in this video, we're going to focus on sine. Just know at any point, you can replace that with cosine because they're interchangeable. They're just shifts of one another. But we had this general transformation that we used for modeling that was a times sine of b x minus c plus d. Importantly in this conversation, what we're going to focus on is instead of having a constant d right here, which keeps the midline at a certain height, we're going to have a function replace that. So over time, our midline could experience growth or decay of some sort. Specifically, we're going to be using functions of this form right here for our changing midline. So the functions we're looking at are f of t equal a times sine or cosine of bt plus g of t. The important focus here is that we're replacing this vertical shift up or down with an actual function that will create change to the midline or the average over time. Before we see an example of an application of creating a model with a scenario that has a changing midline, let's ground ourselves a bit to give us an idea of the kind of functions we're going to be looking at. Here I have two examples, one of a linear midline and one of an exponential midline. What you'll notice in both of these situations is we have these terms that are the oscillation. So the sine in this case and the cosine in this case create this oscillation, this periodic oscillation over time. The significant difference that you're going to see between what we've done previously is in this linear midline right here, the equilibrium is not this flat slope of zero line that goes through zero or is shifted up or down, but instead, over time, the midline is increasing. In fact, for every increase in x value, this is going up by 3, that's the slope. And this plus 5 right here is when x equals 0, that's the starting point. So really, you can think of this whole thing as being our d value or our shift. When x is 0, it's just 5. But as we increase our x value, that midline continues to go up, giving it this positive slope. In exactly the same way, in this model right here, we have 20 times cosine of 2x. So that gives us the oscillation. Again, the 20 and 25 here are these amplitudes. These b values on the inside are changing the period. And we'll talk more about that when we're applying this to applications. But in this case, and you'll see it's a pretty significant difference, we're adding an exponential function. And to remind you of the exponential functions here, this 200 is like this initial or starting point. So this is the starting value. And this factor right here is the exponential factor. This is what's giving it this form right here. And hopefully you've seen these before. Importantly, our exponential factor right here is less than 1, means this is exponential decay, which gives it this look right here. If this factor here was greater than 1, we actually would start at 200 and have an increasing function based on this right here. And in this case, when I read this, I think of this as for every x value increase, this value right here we're adding on is going down by 14%. The way to think about this is we're taking 86% of what we had previously. But importantly, again, when we look at these, first of all, for the linear model, this linear midline, this is the starting value. So when x is 0, we're at 5 right there. So that's like the constant d value. This is increasing for every step. We're going up by 3 along that midline. In this case right here, the 200 is our starting value. And then this designates the decay. Again, this value being less than 1 gives us this exponential shape right here. All right, so here we have an example of a population that we can model with a trigonometric function that has a changing midline. The situation is a population of deer oscillates 15 above and below average throughout the year. So that oscillation is caused by our sine or cosine function that we're going to use, reaching its lowest in January. So that means it starts at a minimum. This in January, we have a lowest population. The average population starts at 650. So that would be where our midline starts, and increases at 160 per year. Find a model for the deer population with respect to months after January. Okay, so our input for this function is going to be months. Let's tackle some of this information real fast. First of all, the first thing I heard was 15 above and below the average, and we know that's the amplitude. So the amplitude is how high and how low you go above midline. So this is our amplitude right here. So our amplitude equals 15. So that's really important, good information. And also knowing that it reached its lowest in January is really important. In this case right here, what I'm going to use is a vertically flipped cosine function because cosine starts at its maximum or minimum. In this case, I'm going to flip it so it's its minimum starting in January. So let's start just basically scoping this out. So we have a population over time. Our amplitude is 15, but I said I wanted a negative 15. So instead of starting at my maximum, I'm going to start at my minimum. And we're cosine right here. And again, cosine, instead of sine, I could have used sine, but then I have to shift it left to right to start at that minimum or the maximum value. Now we need to tackle the period of this function right here. Importantly, we're talking about an input of months, and it seems rational given the information we have that this wants to complete one cycle per year. So it's at its lowest in January, reaches some peak sometime in the summer, and then goes back down to the fall, back into its lowest at January. So we want the period to be one full year. Our input values are months. So in terms of years, so our period, or in terms of months, 1 year would be 12. And we know the relationship between period and the b can be found by this 2 pi divided by 12. So divided by our period and our b, this can reduce down to pi over 6. So what that gives me is this model so far. We have pi over 6x inside of our cosine function. And again, I've taken care of this oscillation of up 15, down 15. The negative cosine makes me start at the minimum value, which I'm looking for, because 0 is the first month, or this is months after January is the way that I'm dealing with this. Now what I need to do is deal with this midline. And so the information for the midline comes from this right here. So it starts at 650 and increases by 160 per year. So what I want to do, and I'll do this on the side, is create a linear model with this information. We know that linear functions are of the form mx plus b. B is this starting value right here. We're starting at 650, so I get that for free. So 650. And now I need to find my slope. So it says that it increases by 160 per year. Importantly though, that 160 is per year. Our x value, our input, is per month. So what we're looking for is to find out how much is this increasing per month. So if we know it is 160 per year, we can find out how much per month by taking that 160 and dividing it by 12. And when I throw that in my calculator, I got 13 1/3 or 13.33 per month. So again, what this is the growth per month. I start at 650 and I have this slope or this growth, linear growth per month of 13 1/3, 13.33. This importantly is my new D value or the change. It's the changing midline that I have. It's not static at 650, but it's increasing over time. So to finish this up, I'll add that changing midline information on here. It's important to say that this might feel a bit intense at first to be looking at this, but it's important to parse this into separate terms. We have the oscillation bit that has to do with how much it's going up and down. Also, this is controlling when it's at its minimum, when it's at its maximum, how often it oscillates. This pi over 6, again, makes it so we have a period of 12, meaning in 12 months, we've reached a full cycle of this deer population as far as the oscillation goes. And this was separate work. Again, the 650 is the starting point. It's the B value for this mx plus b. The 13.33 is just a revised version of the 160 right here. It's 160 per year, but our input is per month. So we need to define this slope in terms of per month. And to finish off, let's look at a visual representation of this situation right here. And hopefully this is what you would expect. We have this oscillation starting at 650 and then rising over time. Every month we're going up by 3. But importantly, we have this oscillation above and below the midline throughout the year.